This video will demonstrate the steps for conducting electrical safety assessment on medical equipment at your healthcare facility. Electrical safety analysis in clinical engineering is the process of conducting tests and evaluating results to ensure the safety of medical devices for both patients and clinical users. This video will cover the basics of electrical safety testing and will demonstrate the test methods and steps to measure protective earth resistance and leakage currents of a medical device. First, we will conduct electrical safety tests using a common electrical safety analyzer. However, many hospitals will not have access to this specialized test equipment. So, we will also cover the steps for conducting electrical safety tests using a digital multimeter, or DMM, and a measuring circuit that is easy to build locally. Please note that there will be limitations to conducting a complete electrical safety test using a DMM. Fewer measurements are possible, it will be inconvenient to set up and operate, and it requires fabrication of a test apparatus. Basics and definitions. The electrical safety test procedures and results depend on the class and type of the medical device under test. The method of protection is defined by the class, and the degree of protection is defined by type. Classes. In Class 1 medical devices, protection is provided by basic insulation and protective earth connection. In Class 2, protection is achieved by 2 or more layers of insulating material between the live parts and the user. Protective earth connection is not necessary in Class 2. Types. In Type B medical devices, there is no intended contact with the patient. In such cases, a standard degree of protection is achieved. Type BF medical devices are safe to be connected to the patient, but not directly to the heart. The applied part of the Type BF device is isolated and must be separated from earth. Type CF medical devices are safe for electrical connection to the heart of a patient. They provide the highest degree of protection against electric shock. The maximum allowable current for Type CF, according to IEC Standard 60601-1, is much lower than for BF or B. Physical inspection. Before you begin electrical safety testing, you must always conduct a physical inspection. Often, you can very quickly find issues that compromise electrical safety with a visual inspection. Faults are commonly seen with power cords, chassis, and device accessories. These often occur due to wear and tear, improper use, and transportation. These images show some common faults that can be quickly identified with a simple physical inspection. Procedure for electrical safety testing with an ESA. To conduct electrical safety tests, you will need medical device under test, electrical safety analyzer or ESA with black chassis lead or cable, and power receptacle with proper grounding. Finally, you will need a checklist to record your measurements. If you do not have access to a checklist, you can use a standardized checklist created to comply with the IEC 60601-1 standards. Now, we will demonstrate an electrical safety test using an electrical safety analyzer on a patient monitor. If you utilize a different manufacturer or model electrical safety analyzer, follow its instructions for use. The patient monitor is Class 1 Type CF. The main difference between electrical safety on Class 1 and Class 2 is that the Class 2 devices are double insulated, eliminating the need for a ground. For Class 1, you will measure the earth leakage current. For Class 2, you do not measure anything involving the ground single fault condition. Before you begin your test, be sure to clean the equipment and your environment. Step 1. Check for the class and type of the device under test. Patient monitors are typically Class 1 or Class 2. You can also check the applied parts to see if they are type B, BF, or CF. Step 2. You should also ensure that your workshop is properly grounded. Then, plug your safety analyzer into a power supply and check that the analyzer's LCD display is on and shows a voltage reading. The safety analyzer should indicate that the incoming supply of power is good and has a proper ground. On your electrical safety analyzer, set your load selection and switch it to IEC. Step 3. Plug in the chassis cable at the chassis connection on the analyzer. Before we connect the chassis cable to the device under test, we will use a self-test to verify that the electrical safety analyzer is working properly. There are 2 snaps on the side of the electrical safety analyzer that you will connect to each end of the chassis cable. They provide a fixed 1 ohm resistance to ground and a 100 microamp leakage current source to ground when the chassis cable is applied and the analyzer is set to the earth resistance and earth ground leakage modes, respectively. If your measurements do not match these typical values, replace your chassis cable. Some variation in values may occur. Please note, the self-test procedure and overall operation should follow the manual of the specific electrical safety analyzer that you are using. Step 4. Connect your device under test to the plug point on the electrical safety analyzer. The device under test will be referred to as the DUT from now on. Step 5. Connect your applied parts to the universal patient lead input of the electrical safety analyzer. For example, this patient monitor has a 5-lead ECG cable. Step 6. Have your checklist ready for the test according to the IEC 60601-1 2nd edition standards. Now we will test for the following parameters: mains voltage, device current, earth resistance, earth leakage current, enclosure or chassis leakage current, lead to earth or patient leakage current, lead to lead leakage current, lead isolation. Step 7. Mains voltage and device current. Set the safety analyzer to test mains voltage. The value should be near 110 volts or 220 volts, depending on your power source. The tolerance is determined by the electrical company, but 10% tolerance is typical. Ensure the device is on for the following tests. Now, perform the same test with current by selecting device current on the safety analyzer. You'll see a value measured in amps. Verify that the measured current matches the manufacturer's specification for the device. Step 8. Protective earth resistance. Connect the chassis cable to the protective earth on the device under test. Select the mode for earth resistance and make sure the clamp is connected to the protective earth connection on the DUT. The measurement should be less than 0.2 ohms. Step 9. Leakage currents. The IEC 60601-1 standard specifies that all leakage current measurements should be carried out in normal and single fault conditions. Single fault conditions simulate a failure in the electrical system. Each of the leakage tests will be performed under several conditions, including normal condition, or NC, open earth, single fault condition, open neutral, single fault condition, reverse supply voltage, single fault condition, reverse open earth, single fault condition, and reverse open neutral, single fault condition. Testing medical equipment in a controlled environment where errors are simulated will help prevent electrical shock to clinical users and patients. Now, let's begin running leakage current tests. Step 10. Earth leakage current. This measures the current flowing through the protective earth conductor under different conditions. Please note that this test is only applicable for Class 1 devices. The test is conducted in open earth mode on the electrical safety analyzer. The electrical safety analyzer should automatically be in the open setting. Compare the measured values with the IEC 60601-1 2005 standard. The measured values should be normal condition, NC, less than 500 microamps, open neutral, single fault condition, less than 1000 microamps, open neutral, reversed mains, single fault condition, less than 1000 microamps, normal condition, reversed mains, single fault condition, less than 500 microamps. Step 11. Enclosure leakage current. This test measures the current flowing to ground through a person who touches any exposed conductive part of the enclosure of the medical equipment. To conduct the test, change mode to enclosure using the arrows on your ESA. Compare the measured values with the IEC 60601-1 2005 standard. The measured values should be normal condition, NC, less than 500 microamps, open neutral, single fault condition, less than 1000 microamps, open neutral, reversed mains, single fault condition, less than 1000 microamps, normal condition, reversed mains, single fault condition, less than 500 microamps. Leakage currents involving applied parts, or AP. We will work with applied parts, or AP, that conduct electricity, such as ECG leads. You do not typically test SpO2 or NIBP. We will measure the patient leakage currents, including lead to earth, lead to lead, and lead isolation leakage current on each applied part. Compare the measured values with the IEC 60601-1 2005 standard. Step 12. Lead to earth leakage current. This test measures the current flowing from a person to earth through the applied part, or current flowing from the applied part to earth through the patient by applying unintended voltage from an external source. Before we begin, make sure the patient leads are attached to the universal patient lead inputs located on the top of the safety analyzer. You can use the patient lead selection buttons to select any individual lead, or you can select all leads as a group to test. Select the mode for testing lead to earth leakage. You will run the test on individual leads and then on the leads as a group. Once you verify that all measurements are within parameters, you can move on to the lead-to-lead leakage test. Compare the measured values with the IEC 60601-1 2005 standard. The measured values should be normal condition, less than 10 CF, less than 100 BF or B microamps. Open earth, less than 50 CF, less than 500 BF or B microamps. Open neutral, less than 50 CF, less than 500 BF or B microamps. Open neutral, reversed mains, less than 50 CF, less than 500 BF or B microamps. Normal condition, reversed mains, less than 10 CF, less than 100 BF or B microamps. Open earth, reversed mains, less than 50 CF, less than 500 BF or B microamps. Step 13. Lead-to-lead leakage current. This test measures the current that would flow from one lead to other leads. Normally, these are auxiliary currents from bias, measurement, and sensing circuits. This test should be done for each lead individually. Select the mode for testing lead-to-lead leakage. Use the patient lead selection keys to select any individual lead to start, and repeat for each lead. Once you verify that all measurements are within parameters, you can move on to the lead isolation test. Compare the measured values with the IEC 60601-1 2005 standard. The measured values should be normal condition, less than 10 CF, less than 100 BF or B microamps. Open earth, less than 50 CF, less than 500 BF or B microamps. Open neutral, less than 50 CF, less than 500 BF or B microamps. Open neutral, reversed mains, less than 50 CF, less than 500 BF or B microamps. Normal condition, reversed mains, less than 10 CF, less than 100 BF or B microamps. Open earth, reversed mains, less than 50 CF, less than 500 BF or B microamps. Step 14. Lead isolation leakage current, also called mains on applied parts, or MAP. This test measures the leakage current that would flow through the patient if one or more applied parts are in contact with mains voltage. This is often referred to as mains on applied parts, or MAP. This test would only apply to F-type applied parts, BF or CF, which are floating or isolated from ground. Select the mode for testing lead isolation leakage. Use the patient lead selection keys to select the leads. You can select all leads as a group and run the test. If the reading is high, you can then choose individual leads and run the tests separately. Once all leads are selected, depress and hold the ISO test key. This will apply 110% of the line voltage through a 121,000 ohm resistor to the selected lead or leads and measure the current that flows to earth through a 1,000 ohm load with IEC 60601 frequency compensation as selected by the load selection switch. Warning: do not touch the universal patient lead inputs during the test, as they can cause electric shock. Step 15. Check if all the test results are inside the appropriate ranges listed on the checklist, and please document your work. If any test result is outside of the proper range, do not return the device for use. This concludes an electrical safety test on a Class 1 patient monitor. Electrical safety for Class 2 devices. As mentioned previously, the test procedure is very similar for both Class 1 and Class 2 devices. The main difference is that for Class 2 equipment, single-fault open earth tests are not required. Therefore, the checklists also indicate which tests can be run for a Class 1 and Class 2 device, respectively. You'll notice that, for Class 2, tests involving earth have been removed from the checklist. Procedure for electrical safety testing with a DMM. While an electrical safety analyzer will make your job easier, you can ensure that devices pass electrical safety tests using a simple multimeter, power receptacles, and a standard measuring circuit, which we will refer to as a measuring circuit. Before performing any tests with a DMM, you will need to create a measuring circuit like the one shown here. The schematic diagram for this circuit is shown later in this video. Extra precautions should be taken when using this method of electrical safety testing. Any modifications to the connectors must be done carefully, as they create electrical shock hazards. This form of testing is limited, and in our demonstration, the following tests will not be performed: device current, earth leakage current with open neutral single fault condition, mains on applied parts, and insulation test. Nonetheless, if you do not have access to an electrical safety analyzer, this form of testing is valuable in ensuring electrical safety. The measuring circuit will allow you to run the following tests: normal condition or NC, forward and reverse mains; open ground single fault condition, forward and reverse mains; and open neutral single fault condition, forward and reverse mains. For best results, use a multimeter capable of measuring down to 1 millivolt. The resolution and accuracy of the multimeter will affect your results. Step 1. Measure the incoming voltage from the power source by using the VAC setting on the multimeter. Verify that this measurement is within 10% of expected incoming voltage. Step 2. For the earth bonding test, make sure equipment is disconnected from mains or unplugged from the power source. Connect one of the leads from the multimeter to the earth connection point of the equipment. Then, connect the second lead to the protective earth of the DUT's power cable. The resistance should read as less than or equal to 0.2 ohms. This is slightly higher than the range given for electrical safety analyzers because a multimeter is less precise. For this test, an ohm meter with good resolution can also be used instead of a multimeter since we are only measuring resistance. For the remaining tests, you will need what we call a measuring circuit. Essentially, it is a multi-plug extension cord where the internal wiring is modified to simulate single fault conditions. Fabrication of the required apparatus should be done by individuals with knowledge of safe electrical wiring techniques and ability to read schematics. The first outlet you will leave intact, and this will be your normal condition. The next plug will be modified to serve as an open earth single fault condition. You'll do this by disconnecting the earth wire found at the top if you're using a UK power cord like the one shown. Tape it to the side out of the way. Next is the open neutral single fault condition. For this one, you will disconnect the neutral wire and tape it out of the way. The neutral will generally be the leftmost prong if you're using a UK power supply. You can confirm this by measuring AC voltage across the prong and ground. The neutral will yield a reading of 0, and the live wire will have a reading. The next outlet is the open neutral reversed mains. For this, you will disconnect the neutral wire and tape it out of the way as you did for the previous outlet. Then, you will disconnect the live wire and reconnect it to the neutral prong. This will reverse the polarity with the ground still intact. The next outlet is the reverse supply condition. For this, you will modify the connection for neutral and live by pulling out both cables and then exchanging or reversing the connections. In addition to the multi-outlet extension cord, you will also need a small measuring circuit to sit between the multimeter and the device, as illustrated here. The recommended measuring circuit consists of a 1000 ohm resistor, a 10,000 ohm resistor, and a 0.015 microfarad capacitor as shown in the slide. This simulates leakage current through a human body. The multimeter setting must have at least 1 megohm internal impedance. The displayed measurement will result in a reading of 1 millivolt, which is equal to a current of 1 microamp. To run each test, you will use the following setup. The MV symbol represents the digital multimeter. You will connect one lead of the multimeter to protective earth. We recommend using earth on the normal condition outlet on the measuring circuit. The other lead will vary for each test. This circuit shows the lead connected to protective earth on the medical device. This is typically at the back of the equipment and will be labeled with the ground symbol. Step 3. This test simulates and measures a leakage current through the ground wire to earth. The test is done under both normal condition and the open earth single fault condition. You will connect the measuring circuit between the digital multimeter and the device under test. Then, you will connect one of the test leads to the external earth point on the measuring circuit. You will connect the other lead to the test point, protective earth, on the medical device. You will plug the medical device into the normal condition outlet, shown as the first in our example. To perform the test, ensure that the equipment is switched on. When you turn on the multimeter, set it to measure voltage. The reading should be less than 0.5 volts, which is equivalent to 500 microamps. Next, we test for leakage current using the single fault condition open earth. To do this, shut off the device completely. Unplug from the normal condition outlet and plug the device into the second plug shown, labeled Open Earth. One of the leads should stay connected to the test point on the medical device, with the second lead staying on the external ground. The DMM should read less than 1 volt, which is equivalent to a current of 1000 microamps. Compare the measured values with the IEC 60601-1 2005 standard. The measured values should be normal condition, less than 500 microamps, and C, open earth, less than 1000 microamps, single fault condition. Step 4. This test simulates and measures a leakage current through the exposed conductive surface to earth. The test is done in normal condition and in the single fault conditions of open neutral and open earth, as well as the reverse polarity, open neutral, and reverse polarity. To test in normal condition, leave one of the leads on the external ground of the measuring circuit. The second lead should be moved from the ground point on the device to any point on the metal body of the device. You can move it around as you test to ensure good readings. Plug the device into the first outlet labeled Normal Condition. Switch the device on. The reading should be less than 100 millivolts, which is equivalent to 100 microamps or 0.1 milliamp. Do the same thing with the device plugged in to each outlet, number 1 through 5. Record values as you go. Compare the measured values with the IEC 60601-1 2005 standard. Single fault condition. Open protective earth, PE, class 1 only. Equipment is switched on, normal polarity, reverse polarity. Leakage current should be less than or equal to 0.5 milliamp, B, BF, or CF. Single fault condition, open neutral, N. Equipment is switched on, normal polarity, reverse polarity. Leakage current should be less than or equal to 0.5 milliamp, B, BF, or CF. The measured values should be normal condition, less than 10 CF, less than 100 BF or B microamps. Open earth, less than 50 CF, less than 500 BF or B microamps. Open neutral, less than 50 CF, less than 500 BF or B microamp. Open neutral reversed mains, less than 50 CF, less than 500 BF or B microamps. Normal condition reversed mains, less than 10 CF, less than 100 BF or B microamps. Step 5. This test simulates and measures a leakage current through the patient connection to earth. The test is done in normal condition and in all 4 single fault conditions. The patient leads of B and BF equipment are connected together and are then measured against earth. In the case of equipment type CF, the currents should be measured separately through each patient connection to earth. As in previous tests, one test lead should be attached to the external ground through the measuring circuit. The other test lead should touch a metal part of the applied part, such as an ECG lead. Start with the device plugged into normal condition and read the value on the DMM when the device is turned on. Your value should be less than 100 microamps for B or BF type applied part, or less than 10 microamps for CF. In this example, the type is CF, so the value measured 0.001 milliamp is acceptable. Plug into the next outlet, open earth, and repeat the process. The measurement should be less than 500 microamps for type B or BF, and 50 microamps for type CF. You'll continue to repeat this process for each of the single fault conditions using each of the 5 outlets. Compare the measured values with the IEC 60601-1 2005 standard. Normal condition. Equipment is switched on. Normal polarity. Reverse polarity. Leakage current should be less than or equal to 100 microamps, B, BF, less than or equal to 10 microamps, CF. Single fault condition, Open protective earth, Class 1 only. Equipment is switched on. Normal polarity. Reverse polarity. Leakage current should be less than or equal to 500 microamps, BF, less than or equal to 50 microamps, CF. Single fault condition, open neutral. Normal polarity, reverse polarity. Leakage current should be less than or equal to 500 microamps, BF, less than or equal to 50 microamps, CF. This concludes your electrical safety test. At this point, make sure you have recorded all of your measurements so you can file the checklist with other records for your device. Wrap up. You've now completed electrical safety testing on your patient monitor. If it has passed the electrical safety tests, remove the connections and prepare for the performance verification test. If the device did not pass one of the tests, double-check the failed section of the test. If verified, you may consider troubleshooting the problem. Otherwise, you can contact the vendor directly or through your administrative process. Do not release a device that has failed an electrical safety test into the field. If the device passes, continue on to performance verification tests. If required, apply stickers showing the date of maintenance or date of next maintenance due. Procedures may vary, so be sure to align with your facility. Record the work completed in both the paper checklist and your digital medical equipment database. Ensure that all fields are complete, making sure to note any dates of maintenance and any issues you found. One final thing you can do once the device has also passed performance verification testing is review the routine care and user maintenance procedures for the device with the clinical care providers. These tasks will help to extend the life of the device. This video is not meant to supplant professional judgment and the need to seek the advice of clinical or biomedical specialists, particularly for discussion and evaluation of complex cases. World Health Organization expressly disclaims responsibility and shall have no liability for any damages, loss, injury, or liability whatsoever suffered as a result of your reliance on the information contained in this video. World Health Organization does not endorse specifically any device, company, test, guideline, treatment, or procedure mentioned in this video.